Okay, so it's a pleasure to introduce Ben Steinberg from University of New York, who will talk about Cartan pairs of algebras. So please, Ben, go ahead.
All right, I want to thank the organizers so much for giving me a chance to speak here. It's nice to speak at a non-commutative geometry seminar. You know, I should put little warning that I'm an algebraist who's kind of dabbling in stuff that's connected with analysis. So, but I'm not an analyst. So if I say anything wrong about the analytical part, blame me and not my co-authors. So as you see, I have a long list of co-authors here. We started off as two separate teams and then we discovered we were working on the same thing. So we decided to join together rather than race to have two separate papers. And I think it's better that way. I think that what we were doing to some extent overlap, but other extents complemented each other. So I think it ended up being good that we all joined together. I still haven't actually met everybody on this list in person because once we joined forces, we were already in Zoom mode. So, so one day, hopefully I'll actually see everybody in person. Okay, let's see, hold on. All right, it is turning. All right, so there's the outline of the talk. There's 3 parts, but let's start with the analytic origin. So this is the part where I'm a little bit fuzzy on. So if I say anything wrong, I am sorry about it. So Cartan pairs, well, of course, Cartan pairs really started in Lie theory in the sense that you have these Cartan subalgebras, which are maximal abelian subalgebras. And then in the 60s, Feldman and Moore studied Cartan pairs in the setting of von Neumann algebras. And most people in this know the theory probably better than me, but basically, roughly speaking, you have a von Neumann algebra A and a maximal abelian or commutative subalgebra algebra B, which sits nicely in A in a technical sense, which you can make precise. I don't want to get into it. In the algebraic setting, we try to imitate a lot of these niceties, more like the C-star version of it than the von Neumann algebra version of it. But anyway, the main result or upshot is that Cartan pairs come from certain sort of twisted groupoid algebras, but the measure theoretic version of these things. For appropriate groupoids, they were actually essentially equivalence relation groupoids, and the commutative algebra functions on the unit space. And I mean, in this setting, it's a little bit better because these Borel equivalence relations come from group actions. But anyway, the groupoid point of view, they emphasize the groupoid point of view. And the groupoid and the twist are uniquely is in quotes because uniquely up to the obvious equivalence relations determined by the Cartan pair. Later on, I wrote Kumjian and Renault, but it's kind of like in succession. First Renault started it, and then Kumjian improved it, and then Renault re-improved it. And they created a C-star algebra version of the theory of Cartan pairs. Again, you have some sort of C-star algebra and a maximal commutative subalgebra that sits inside it nicely in a certain sense. And then they prove that these kinds of Cartan pairs come from twisted groupoid algebras or algebras of twists. Renault started more with the classic twisted groupoid algebra, and then Kumjian came up with the right notion of a twist. And they come from étale groupoids, so groupoids whose groupoid structures via local homeomorphisms, the domain, the range, the multiplication, everything in sight is a local homeomorphism. And they're a special kind of étale groupoid. It's not just any old étale groupoid. And again, the groupoid and twist are unique in an appropriate sense of what it means to be unique. All right, but for a long time, this kind of sat here as a theory, but then people started recently, especially Matsui and Matsumoto, started to apply this theory, in particular to symbolic dynamics. So as most people here know, I don't think I need to say much about it, a shift of finite types, a dynamical system associated to a finite directed graph. You can generalize this in various directions, but roughly speaking, you have the set of infinite paths on the graph. You can either do the two-sided shift where you have two-way infinite paths, or the one-sided shift where you do one-way infinite paths, and you have the shift map. And it's long been known that there are connections between a shift of finite type, the graph C-star algebra of the corresponding graph, and the Leavitt path algebra, which is the algebraic version of a graph C-star algebra, where if you're a ring theorist and someone hands you the defining relations of a graph C-star algebra, you say, hey, wait, I can make this a ring. And then this is the name Levitt's associated because for the case of the Kuntz algebra, Levitt introduced the corresponding algebra actually before Kuntz, completely both of them unaware of each other's work, of course. And then, for instance, one of the main examples that I think shows you that this connection is interesting is that the Bowen-Franks group of a shift of finite type, which was introduced by Bowen and Franks to study, flow equivalence or conjugacy of shifts, is both the K0 group of the graph C-star algebra and the Levitt path algebra over any field. It doesn't matter which field you do. If you don't do it over a field, then I think there might be little subtle differences, but maybe integral domains even good enough. But and under condition L, so condition L, roughly speaking, is kind of like this condition 2 in the original Kuntz-Krieger algebras. Basically, you want to avoid cycles without an exit, or you don't want strongly connected components which are cycles. So that's what you need to avoid. Under this condition, the graph C-star algebra and the continuous functions on the path space, the one-sided path space, form a Cartan pair. And Matsui and Matsumoto, that's what MM stands for. Their names are long, so I didn't want to go off the end of the slide, but it was already said at the top. They characterize continuous orbit equivalence of shifts of finite type by the isomorphism class of the Cartan pair. By isomorphism class of a pair, I mean that the big algebra should be isomorphic to the big algebra in a way that sends the subalgebra to the subalgebra. And they also observe that flow equivalence can be determined by basically replacing your graph by a certain infinite graph that lets you take into account stable isomorphism, roughly speaking. And so, they kind of came up with sort of an application of this sort of Cartan pair stuff to the dynamical world. And a bunch of people kind of asked the question, can the same be done for the Levitt path algebra? Can I recover this dynamical information from the Levitt path algebra? And so Levitt path algebras are algebras of certain ample groupoids. Ample groupoids are groupoids where the unit space is totally disconnected. And people are calling these things Steinberg algebras because nice people, I guess mostly it was Lisa Clark, so I should thank her. I was sort of, I guess, the one who said we should spend time looking at the purely ring theoretic versions of these, but the definition is basically the same as it would be in the C-star setting. You just don't complete. So anyway, I usually call them groupoid algebras, but that's why I put it in quotes. Anyway, there was a series of work by a bunch of authors. First, there was work by Brown, Clark, and N.F., which they were looking at just the case of Levitt path algebras. Then Aza, Boza, Hasvad, and Sims were looking more generally at groupoids, but Levitt path algebras were certainly on their minds. Then Carlson and Rout kind of extended their results in the groupoid setting. And then I kind of got, I think, what's the ultimate thing you can do in determining when a groupoid, ample groupoid can be recovered from its algebra and its canonical commutative subalgebra. And in particular, in the case of a Levitt path algebra, we saw that you can recover the groupoid of the algebra from the groupoid algebra, but the ring theoretic analog, which will be the Levitt path algebra in that case, and the commutative algebra. So in the Levitt path algebra setting, what lives inside the Levitt path algebra is not all continuous functions on the path space, it's just the locally constant ones. In the algebraic setting, you can't deal with continuous functions which are not locally constant. That's basically the difference between the algebraic world and the analytic world. You can do analysis, right? Remember, we're allowed to work over the 2-element field. So what else can you do besides look at the discrete topology on the 2-element field? There's no other reasonable topology. Okay, well, maybe some non-Hausdorff people like other topologies, but that's the only topology I'm willing to look. And what's funny is that in the algebraic setting, you don't need condition L anymore. You can weaken the notion of Cartan pairing, and you don't quite need it to be maximal commutative subalgebra. You can get away with something a little bit weaker. And so you can actually throw out condition L and still get the groupoid. And actually, Carlson had a beautiful result where he showed that the groupoid is determined by the Levitt path algebra over the integers as a star algebra without even caring about the commutative subalgebra, just from the ring theory, which is kind of interesting, but he does need the star operation. And so, and again, you can get analogs of the results of Matsui and Matsumoto without condition L by basically using that the groupoid can be recovered from the algebra, but now you would use the Levitt path algebras instead of the graph C-star algebras. But one thing that was missing in all this was a theory of abstract Cartan pairs. So the situation that was looked at by this group of 4 authors, well, 4 series of authors, is given when can you recover an ample groupoid from its algebra and the algebra on the unit space? But nobody asked the question, which pairs of algebras actually come up from groupoids? And so that's kind of the question that we were interested in. Is there some sort of abstract Cartan theory that says, you know, if someone handed you the Levitt path algebra and you didn't know that there should be a groupoid out there, then there is a groupoid out there. So that's kind of the setup we're looking at. But because of my background originally was more from group theory, I figured we should start with groups, because after all, groups are one object ample groupoids, right? You can say that a groupoid is kind of a group with an identity crisis because it has many identities and the group only has one identity. And it's amazing how group theorists do not like groupoids because of this identity crisis issue, but groupoids are nice. So let's start with, and groups, discrete groups are ample because, well, they're totally disconnected, obviously. So let's start there. So, and in this talk, my ring R will always be an integral domain. In our paper, we actually work over more general rings, but I just don't want to get into like technical commutative ring theory because probably you guys don't care about anything more general. The integral domain is nice enough. I mean, there are interesting rings that are not integral domains, but let's leave it there. But we do have results over non-integral domains. I just don't want to get into it. So the classical isomorph asked, actually, I think mostly to Grant Higman's thesis, if you have 2 group rings which are isomorphic as R algebras, are the groups isomorphic? So R is the diagonal subalgebra. It's the algebra of the unit space of this one object groupoid. You have only one object, so a locally constant function from one object to R is just an element of R. So in the group setting, we're basically asking, can we recover our group from the group algebra? And this is the simplest state version of what we want to know for groupoids. Now, if you've ever been forced to teach any sort of either representation theory or Fourier analysis or anything, the first thing people learn is 2 finite abelian groups of the same order have isomorphic complex algebras by basic Fourier analysis. So you cannot recover a group from its group algebra. Certainly you can, and groups are kind of particularly bad from this. If you think about the whole Cartan setting, they're pretty bad for this. So clearly the complex numbers is way too big. Sorry to say that to analysts, but for this question, it's too big. So a better question to ask is maybe if the integral group rings are isomorphic, then the groups are isomorphic. Because of course, as soon as the integral group rings are isomorphic, all the other group rings are isomorphic. So if this is sort of the one group ring to rule them all, to make my Lord of the Rings joke. So this is your best shot. And so for a long time, people actually tried to prove this for finite groups. And they had a fair amount of success. They proved it for finite abelian groups, and then they went up the hierarchy of, different classes of finite groups. And then Brouwer began to be suspicious that this is just wrong. And he kind of gave a program on how to show it's wrong, but it's wrong. Really, I didn't see the change on the screen. Did I freeze or something? Let's see. Am I still here? But it did show up finally.
Yeah.
All right. I guess there's some.
You should make it full screen again.
I did, but there seems to be a delay on my laptop here. I guess my internet connection is not great. So Hertweg found in a paper published in Annals in 2001 2 non-isomorphic groups of this ridiculously big order. The numbers I wrote down are correct. With isomorphic group rings, but the groups are not isomorphic. So in particular, you can never recover these groups from their group rings no matter what base ring you use. Okay, so these are like, ridiculously large groups. You obviously didn't find them by a random search. You would never find this by a random search. You could spend your whole life doing this random search and you will not find it. As far as I know, there's only one general method to show that a group algebra determines a group. And this is the method of trivial units. So if you have a unit U from your ring and you multiply it by a group element, then that's obviously a unit. And these are called trivial units. And we say RG has no non-trivial units if the only units are these obvious ones, the trivial ones. And you can make the same definition for twisted group rings as well. And for twisted group rings with only trivial units, you can recover both the group and the twist from the group algebra as an R algebra. And I'm going to show you how to do this because our general proof is basically, you know, a fancy souped up version of this. So if you understand this, you get the main idea, but it's a lot easier for groups. So a twisted group ring is you have a normalized 2 cocycles. So this audience knows what cocycles are. And then you basically make a base group. You make a ring which is a free R module with basis and bijection with the group. But when you multiply 2 group elements, instead of getting a group element, you get this twist times the group element.
One little question. Your group doesn't act on the coefficients, does it?
No, it's a twisted group ring, not a cross product or a skew group ring. The group does not act on the coefficients here. A good and important question, but no, we haven't gone there yet. And we haven't gone that way with groupoids yet either, although you could. Maybe Tristan has already gone that way, but and of course, if the cocycle is trivial, you just recover the group ring. And then again, because the group is not acting and all this kind of stuff, a unit times a group element is another unit, and this is the group of trivial units. And you actually have a central extension. The multiples of the identity live inside as a normal subgroup, and the quotient is G. And it's exactly the central extension which is classified by this cohomology class. If you have a cohomology class, it gives you a central extension, and the extensions are equivalent if and only if the cocycles are cohomologous. And so if we want to recover the cocycle, we need to just recover this extension, yeah?
So for you, the R was commutative all the time. When you said domain, you meant
R is commutative. Yeah, sorry. I said it was an integral domain. You can also allow rings not to be commutative too. Yes, you can also do that. There are all sorts of directions you can generalize. Since we want our Cartan algebra to still be a commutative algebra in this case, we want R to be commutative. But again, there are probably good reasons to go beyond that case. So yeah, so our R is commutative, and it commutes, and G it commutes with G. So G is an R algebra. So the twisted group ring is an R algebra, a commutative over the commutative ring R. And so we'll say that the twisted group ring has no non-trivial units if the only units you have are the obvious ones. And then if the group ring has no non-trivial units and you have an isomorphism of some other twisted group ring with it, then you're going to get a morphism of these exact sequences. Why? Well, our isomorphism has to take units to units. But the only units that the group ring for G has are trivial ones. So our diagram must go like this. And the middle guy is injective because this was a group isomorphism. But since the multiples of H span the group algebra of H, their image must span the group algebra of G under an isomorphism. And that means you cannot miss any multiple of G. So this actually must be surjective. So you recapture this exact sequence. And therefore you recapture G and the cohomology class. So it's very simple to recover the group. I'll just leave it there for a second while I get a drink. I mean, you know, during a talk at 3 p.m. or whatever time it may be, wherever you are, maybe it's not so easy, but it's really very easy to recover the twist when G has no non-trivial units. Okay, I mean, I saw this argument in Passman's book for classical group rings, but it's very easy. The twist doesn't play any extra additional role. So which group rings actually have no non-trivial units? Well, as many people know, this has become a big deal quite recently. So the only known property which guarantees no non-trivial units is what's called the unique product property, or UPP. And I'm not going to define that. Roughly speaking, it's exactly the property you need to guarantee that there are no zero divisors in your group ring. It says that if you have 2 finite subsets of your group and you multiply them, then somebody in the product set should be uniquely expressible as a product in one set and the other. So that way, when you kind of multiply 2 elements of the group algebra, you're guaranteed one term survives. And then it's a clever result of I can't say his name properly, Steinberg, I can't say it right, that actually you get two unique products. Anyway, the main examples are left orderable groups. And for left orderable groups, it's easier to show they have no non-trivial units because you kind of, when you multiply two elements, you look at where things stand in the order and you can figure out what happened and not too much cancels out. So in particular, torsion-free abelian groups, free groups, braid groups, all these guys have unique product property. Yes, question? Question, Guillermo? No?
I wasn't asking.
Oh, I thought I saw your hand up.
But yeah, okay. So I just thought, since you stopped, to mention that we had Gardam give a talk in this seminar.
Yeah, I was about to mention his result. I saw he was here
Yeah.
last week. I always seem to talk a little bit after him. The last seminar I talked, it was also. So UPP groups are torsion free. But let me just point out, these are not the only groups with no non-trivial units. For instance, Higman proved that if ZG has no non-trivial units, then if you take a direct product with a cyclic group of order 2, you still have no non-trivial units. So you can have torsion. The other Kaplansky conjectures are dead by torsion, but not this one. Well, he didn't conjecture, but you could have their property. And Higman also showed that the finite groups which have no non-trivial units are abelian groups of exponent 4 or 6 or certain quaternion groups. So as was just mentioned, so Kaplansky's unit conjecture said that, which was actually, I think, first sort of stated, maybe not quite as a conjecture, but asked about by Higman in his thesis in the 40s, is if G is torsion free, RG should have no non-trivial units. But Giles Gardam placed an archive at the beginning of the year, a counterexample of a certain virtually abelian group, torsion-free free abelian group, so a torsion-free group with a free abelian subgroup, who had a non-trivial units over the 2-element field, and that's been extended since by, I think, Murray, or I think maybe I have the name wrong, to all prime characteristics, but it's still not known about characteristic 0, which is probably the most interesting one. In any event, it means that the no non-trivial units phenomenon is less widespread than previously hoped for. Believe might be too strong a word. I'm not sure how widely believed the unit conjecture was. Nobody's going to claim they believed it now that it's been disproved. So now I'm going to turn to groupoids. So this is an audience that probably knows all about groupoids, but anyway, just in case you don't. So I like this terrible definition that a groupoid is a small category where each morphism is an isomorphism. So what does that mean? Oh, and I'm going to follow the analyst convention and identify identities with objects. So G0 will be the set of identities or idempotents, as I like to think of them. And basically what you have is a set with with a bunch of identity elements and a partially defined multiplication and an inversion map that behaves like a group except for this phenomenon of multiple identities. And from this viewpoint, notice the domain map and the range map can be written in terms of multiplication, right? So the way, in case you're not an analyst and you're used to the algebraic way of thinking of this, I think of course, an element of a groupoid should be an arrow from its domain to its range, but I'm going to identify this. Oops, that's not an alpha. I'm going to identify this with the corresponding. All right, maybe I did an eraser. Oh, now it worked. I think I have a very slow internet connection here, or somebody else is using the internet. So I'm going to identify the domain with the identity at the domain, which is this element, and same for the range. Okay, and then the identity form a subgroupoid in which everybody is their own domain and range, and they square to the identity. And a group is the same as a groupoid with a single identity. But to build algebras which are interesting, you always need to put topology on your groupoid. If your groupoid is discrete, then the algebra is just a direct sum of matrix algebras over group algebras, and you get nothing new. So a topological groupoid is a groupoid with a topology that make the multiplication and the inversion maps continuous. And all my groupoids in this talk will be Hausdorff. One shouldn't do that in practice, but for now they're going to be Hausdorff. Eventually this will probably be removed. But right now the Cartan pair, even in the C-star setting, the Cartan pair notion without the Hausdorff condition is kind of still being developed by people like Pitts and Exel, and then Meyer and some of his co-authors whose names are slipping my mind. So it's still kind of in progress in the non-Hausdorff case. I'm always going to give the unit space, the subspace topology, and then of course the domain and range are continuous. And G is a tau if the multiplications and local homeomorphism are the domain or the range or anything else involved is a local homeomorphism, except the inverse. The inverse, of course, always is a homeomorphism. But as soon as anything else is a local homeomorphism, everything is. Tau groupoids actually, last time I gave this talk, I said they were introduced, but after Tristan attacked me on this, they're essentially introduced, even though the topos theorists all say that it was introduced by Grothendieck in the exercises of SGA. He does a tau equivalence relations, he does transformation groupoids for groups acting on spaces, and then he kind of has something else that if you are fancy at category theory, kind of includes the rest, sort of. But anyway. And the groupoid is ample if it's a tau and it's locally compact and totally disconnected. And that's the only case I care about here. And because my groupoids are Hausdorff, remember that G0 is always Klopen. So, I mean, maybe these examples are not so important for this seminar. So a topological group is a tau precisely when it's discrete. You can make any totally disconnected space an ample groupoid of identities. If you have a discrete group acting on a locally compact, totally disconnected space, you can take the transformation groupoid, which is an ample groupoid, and I think everyone knows this here. So you just take the product with the product topology, and you basically draw the Schreier graph of G acting on X, and then you notice that because with all the group as generators, and then you notice you can multiply them as long as we use the whole group for our Schreier graph. So that's and then the topology, and it's easy to check that the projection is a principal G bundle, so it's certainly covering space, and therefore a local homeomorphism. And so these are the standard examples everybody gives. There's also the path space of a graph, but I don't have time to define that. If you know it. So the way you define a groupoid algebra.
Froze.
I'm sorry?
No, that you just froze.
I froze. Am I still frozen?
Yeah. No. Not yet. No.
Okay, sorry for the technical difficulties. Yeah, I recently moved and there's only one internet company that services this area and it's not very good. Okay, so if you have a Hausdorff ample groupoid, then and your ring R, which can be, I mean, for this definition, the ring R can be any ring, but for us, it's going to be an integral domain. What you just do is you take CCGR, the locally constant functions with compact support. So essentially you give R the discrete topology, you look at the continuous functions from G to R, and these will be the locally constant ones, and you ask the support is compact. Since it's locally constant, the support is really just the things which do not map to zero. It's already going to be closed. And then you do the convolution product. And because the groupoid is a tau and the support's compact as usual, this is a finite sum. And so, and inside of here, you have the algebra of the unit space, which is just the locally constant functions with compact support with pointwise multiplication. And this lives inside here, and it's a commutative subalgebra. And there are lots of examples. Group algebras fit into this context because a group, since it's discrete, a locally constant function with compact supports, just a finitely supported function. And then this convolution is the usual group algebra multiplication. Levitt path algebras you can get by using the path groupoid and doing this construction. If you're willing to allow non-Hausdorff groupoids, you can get all inverse semi-group algebras. You can also get matrix rings. If you do this to a transformation groupoid, you get a skew group ring. The group GX on the continuous functions or the locally constant functions from X to R, and you can form the skew group ring, which is what you get in this context. So there are lots of examples, but we also want to twist them. So I'm going to give you a slightly simplified version of a twisted groupoid algebra, which is good enough for most purposes, just to make things easier. Although with this audience, I probably don't need to. So if you have a locally constant 2 cycle from the composable pairs to the units of R. So this is a standard 2 co-cycle condition. So in particular, notice the groupoid does not act on the coefficients. And we only need to make sense of this when you can multiply. And I'm going to assume that the cocycles normalize, which means that on a unit, comma unit, it's 1. That implies on a unit, comma anything, it's 1. But then we can form the groupoid algebras before. We can take the locally constant functions with compact support, but now we can twist the product by the cocycle in the standard way you would do for a group. And you still have the algebra of the unit space living here because I made the cocycle normalized. So if alpha and beta are units, then you don't twist. And this, of course, generalizes a twisted group ring. And in fact, this is not the real definition of a twisted groupoid algebra. To give the real direct definition, you need to take a twist and then do the sections as a line bundle or one of the other various approaches to that. But because we're dealing with totally disconnected groupoids, if it's second countable or paracompact, then you always have a global topological section and you can get the cocycle. But there are examples where you have no, if your space is big enough, if the unit space is weird enough, you might not have a section. I know most people in analysis only work with second countable groupoids, and so you assume that ample means you have a section, but it's not true. We give an example in our paper where there's no section, but we rely on some paper by commutative algebraists where they construct a non-trivial principal bundle over a totally disconnected space. So we need to use something to do that. Okay, so roughly what we're interested in is knowing when we can recover. By the way, let me see how I'm doing on time. Probably very badly on time. I'm usually doing badly on these Zoom talks. I can't even see my clock. Okay, so we want to basically know when can we recover G from the algebra and the commutative subalgebra. Okay, when you have a group, the corresponding pair would be your twisted group ring in R because the algebra of the unit space is R. And we saw in that case that if you have no non-trivial units, you can recover the group and the twist. So what's the correct analog of units in the groupoid setting? Well, if you're familiar with Cartan pairs from Feldman-Moore and from Renault and Kumjian, you're going to say normalizers. So the correct analog of the units are the inverse semigroup of normalizers of B. And so the other thing we would like to know is which pairs of algebras consisting of an R algebra A and a commutative subalgebra B actually come about from a groupoid pair, or at least one which is sort of Cartan-like. So those are the two questions that we're interested in this talk. So now I'm going to give you our setup for the rest of the talk. R will be an integral domain commutative. Again, you can do weaker stuff, but I'm going to make life easier. A is going to be an R algebra, but it's not going to necessarily be unital. B is going to be a commutative, torsion-free R subalgebra generated by idempotence and containing a set of local units for A. And I'll write the definition of local units. So local units is the ring theoretic version of approximate identity. So in the C star setting, you would want the commutative subalgebra to have like an approximate identity. For A, local units is the closest you can do in ring theory to an approximate identity. What it means is that for any finite subset of your algebra A, there should be an idempotent to B so that E acts as an identity on your finite set F. So the E is kind of for, and since the ring B is commutative, the idempotents are directed, so they form a kind of net of identities. Okay, so that's the condition. Torsion-free is just a sense of module theory. No non-zero element of my ring R annihilates any non-zero element of B. So the usual torsion-free from when you teach algebra, if you teach algebra and you do modules over a PID and all that kind of stuff. So for example, if A is a twisted groupoid algebra and B is the algebra of the unit space, you have these conditions. The local units are just the characteristic functions of compact open subsets of the unit space. The characteristic functions of compact open sets are idempotents and they generate B. So you're in this setting. And so I'll call pairs like this a groupoid pair. And basically we want to know when does the groupoid pair determine the groupoid and which things are groupoid pairs. So what is a normalizer? So we have to, in the algebraic setting, we don't have star. So we have to kind of work around star. So a normalizer B is an element N of an A, which has an inverse type element N prime, which satisfies sort of the von Neumann regular inverse condition, so the partial isometry type condition, but we don't have star. And it should conjugate, so N Bn prime and N prime Bn should be contained in R. So in the C star setting, you would ask that N prime should be N star, but we don't have a star.
But so I mean, you could consider star algebras without completion.
You could, but we don't want to force that.
Okay.
You could, but we don't want to make it part of the definition.
Mm-hmm.
Right? Because, you know, maybe you didn't realize your algebra is a star algebra ahead of time. I mean, at the end of the day, if you come from a groupoid pair, then it is a star algebra. But we can talk about normalizers even if there was no groupoid pair. Okay, so the normalizers under our setting form an inverse subsemigroup. So an inverse semigroup is a semigroup where every guy N has an N prime so that those two properties holds. That's the definition of an inverse semigroup. Or it's a von Neumann regular semigroup where idempotents commute. So for instance, if you take a twisted group ring, RGC, and you look at the normalizers of R, basically what you get are the units and 0. And so the normalizers do generalize units. Obviously 0 normalizes, so you can't get away from that. And the groupoid algebra is spanned by normalizers because if you take a bisection, so a local bisection is just an open subset where the domain and range maps are injective. This is an audience that knows what that is. Then the compact bisections form a basis for the topology. They are normalizers and they span the groupoid algebra. So the normalizers span, which is the kind of thing you want in the C star Cartan setting. In a group, a bisection to all the arrows in a group have the same domain and range. So as soon as you have 2 arrows in a set, you're going to break the domain being injective condition. It's also more or less obvious if you have a locally constant function whose support is a bisection, and on that bisection it takes on values in the units, then you get a normalizer. And these are the trivial normalizers. This is basically the same argument that if you multiply a group element by a unit, you get a unit in the group ring. It's the same argument, basically. So the obvious generalization of no non-trivial units is no non-trivial normalizers. All your normalizers should have support a bisection, which if you're familiar with the Cartan theory for C-star algebras, that comes up all over the place. So we make this a definition. So we say the twist satisfies the local bisection hypothesis of the support of any normalizer of bisection. This name, local bisection hypothesis, maybe not a great name. Maybe I should have called it the no non-trivial normalizer thing. I first came up with this name when I was in the non-twisted case. And I think I didn't immediately recognize that the relation with non-trivial units until later. And then I already had this name stuck in my head. So in retrospect, it should probably be called no non-trivial normalizers or something. So a twist on a group satisfies this local bisection hypothesis precisely when the units are all trivial. So there's a generalization. So this is a generalization of the no non-trivial units. And it's actually very connected. So if you have any object, you have the isotropy group, the morphisms from X to itself, that's a group. And it turns out if you look at the objects or the units for which the isotropy group is a UPP group, so let's say left orbital or satisfies the Kaplansky type stuff, if these are dense in the unit space, then automatically for any twist, you get this local bisection hypothesis. So said differently, having this sort of Kaplansky type property for the group, the isotropy groups, for enough of them, gives it to you for the groupoid. So what does this give you? Question?
Yes, but I mean, the Kaplansky hypothesis would be that there are no non-trivial units in this in the group algebra. But so this is a property. UPP implies that, but it's not equivalent to it.
Yeah, what we actually need in this is basically that for any cocycle and any integral domain, you should have a dense set of isotropy groups where you always get over R. you should be guaranteed a dense set of units where you have no non-trivial units, but that's too messy to state. So here's a sufficient condition. But basically, if Kaplansky conjecture is satisfied for a dense set of objects, then, but Kaplansky, where you're allowed to throw in cocycles. I mean, I don't know if there's any example where you have non-trivial units, no non-trivial units in the standard group ring, but not in twisted group rings. Since UPP gives you twisted group rings, they're fine too. I don't know if we've proved that, but it's the same proof. So for instance, if you take the groupoid associated to a Leavitt path algebra, the path groupoid, it's well known all the isotropic groups are either trivial or infinite cyclic. The isotropy at an ultimately periodic point is infinite cyclic, and at an aperiodic point is trivial. These are left orderable groups. They're free abelian groups. And so, they satisfy the UPP property. They're as good as can be. So that's why you get it for the Leavitt path algebra, and you do not need conditionality. So we're going to say that you have a concrete quasi-Cartan pair. If you have a groupoid with a twist and it's commutative subalgebra, and you have this no non-trivial normalizer, local bisection hypothesis. So these are the concrete quasi-Cartan pairs. Then, of course, we want to axiomatize which pairs of algebras come up that way, if I'm lucky. So to do that, we have to talk about conditional expectations. That's probably not a surprise if you're an analyst. So if you have a group ring, there's a Frobenius.
Where's my iPad?
It's over there, sorry. So if you have a twisted group ring, if you have a group ring, you have a standard functional, going back to Frobenius, called the Frobenius functional, which takes the coefficient of the identity. And that's the retraction to R, and it has great properties that Frobenius already knew about. And we need to generalize that. So suppose that A and B are in our general setup where we have, B is generated by idempotence, has local units for A, etc. So a conditional expectation is just an R linear map from A to B, which fixes B, and it's a BB bimodule homomorphism. So it's like the definition in C-star algebra theory, except we remove all the analytic conditions because we can't define them. And then it's called faithful if for every A, there's an A prime, so that this happens. And this kind of conditional is also actually appears in the definition of Frobenius algebra. So people in ring theory also look at conditions like this. So for instance, if you have a groupoid pair coming from a twist and you restrict to the unit space because we're Hausdorff, that's a legitimate thing to do. And this gives a faithful conditional expectation. And this is a generalized twisted group ring example. And this algebraic notion is due to Watanabe. Okay, so now I can tell you what is an abstract quasi-Cartan pair. The definition is a mouthful, so I don't expect you to absorb it, but Guillermo will put up the slides so you can eventually absorb it. This paper also will be coming out someday. It was recently, finally, the proofs were sent in to IMRN, or I hope I got the acronym in the correct order. So we're going to add a new condition. We're going to assume that the normalizers span A over R. That's what you would do in the C-star setting, right? You want the normalizers to generate a dense subalgebra. We can't do dense, so we just say span. And we want a faithful conditional expectation. Question? Okay, so we're going to call it a Cartan pair. So we're going to call it a Cartan pair if B is a maximal commutative subalgebra. So we need to have the normalizer span, the faithful conditional expectation, the local units, which is like the approximate identity, and the maximal commutative. The quasi-Cartan pair is a little bit more delicate, so I don't expect you to absorb it. But what it means is that when you do, you can choose the conditional expectation in such a way that for normalizers, you can implement it by multiplying by an idempotent of B. So multiplying by an idempotent of B corresponds to restriction in the world of inverse semigroups. So this is sort of saying that your conditional expectation on normalizers behaves like restricting functions to the unit space. So that's the moral. So saying it again, this is an inverse semigroup. This is a sub-semigroup. In an inverse semigroup, multiplying by an idempotent corresponds to restriction of partial isometries. And so we want to say that the conditional expectation is given by restriction.
So
it turns out Cartan. So it turns out Cartan pairs are quasi-Cartan,
okay.
but it takes a little bit of work. It's some clever argument that I don't remember. There's some clever argument. It's like idempotence commuting in an inverse semigroup. It's true, but it's one of these clever arguments that's not so easy to remember. And also, it turns out quasi-Cartan pairs have a unique conditional expectation. And the groupoid pair is quasi-Cartan exactly when you have this local bisection hypothesis. So in particular, for groups, you get this condition, abstract condition, precisely from the no non-trivial units. So you can just go in and you can take the conditional, you can just check that the only way the conditional expectation of taking the coefficient of 1 actually is given by restriction is because you have only one guy in the support of your normalizer. Otherwise, it doesn't work. And when is it Cartan? It's the usual condition. The groupoid should be effective, meaning the interior of the isotropy is G0. You have to be slightly careful if your groupoid is not second countable. This is not the same as saying that as being topologically principal or the various other things that people use as synonyms for effective. You need this one. As soon as you allow groupoids that are either not Hausdorff or not second countable, all these different things diverge, and you have to be careful to get them right. So here's an example that I used when I gave this talk for algebraists. Of course, everyone knows this one who's an operator theorist. You take n by matrices over R, and you take the diagonal submatrices as B. The diagonal submatrices are spanned by the idempotents, the EIIs. The Mn of R is spanned by the EIJs, which are normalizer, and their inverse is just the EJI, the transpose. It's in fact really a star thing. And the full normalizers are what I would call monomial matrices with entries in R cross. So all your non-zero entries should belong to R cross, and you never have two non-zero entries in any row or column. Some people call these rook matrices because the non-zero entries look like rooks on a chessboard. They're not attacking each other. And this guy is a maximal commutative subalgebra. That's pretty obvious. And your conditional expectation should be just take the diagonal. And this is a Cartan pair. And of course, we all know the groupoid that gives it, right? You just have n objects and exactly one arrow between any two. So now I can tell you our theorem with our AC cubed LMRS squared authors. Do not quiz any of the authors to list all the authors all at once. So there are two theorems. So the reconstruction theorem says that if you have a quasi-Cartan pair, then there is a twist over an ample groupoid G and an R linear isomorphism of pairs that sends A to the twisted groupoid algebra and B to the corresponding subalgebra. And the twist is unique up to equivalent, meaning that if you find two G's and cocycles, or actually they should be genuine twists, not necessarily cocycles, then you have the corresponding isomorphism of the groupoids and twists. So the correct diagram commutes. So this is sort of the, I think I said, no, that's all I say here. So this is sort of the main result. So as I said, if you don't throw in twist, part 2 was known. Namely, if you had a groupoid which satisfied the local bisection hypothesis, it was known that you could recover the groupoid from its algebra. That was my theorem from, I don't know, 2018 or 2019 or 2017. I don't remember when it came out. But we didn't have this theorem. First of all, we didn't allow twist. And second of all, we did not have this theorem that you can build a twist from an abstract algebraic pair. And that, that's certainly I never would have thought to do. So I'm very thankful for my analyst friends who understand this kind of stuff. So I think it was really nice. And I certainly learned a lot working with all these people to come up with this. So this is really what our main result is. I will just say a little something about how I think about the proof. It's not actually the way we wrote the proof in the paper. It's more the way I wrote the proof in the non-twisted case, but this is how I think about it. The point is, if you have a quasi-Cartan pair, you get an exact sequence of Boolean inverse semigroups. Boolean inverse semigroups are inverse semigroups as idempotents from a Boolean algebra, and there's some distributive law of the products over the Boolean algebra. Anyway, what you have the normalizer in A of B, then you can look at the sub-inverse semigroup of diagonal normalizers. And then this is because the normalizer of B normalizes B, this is a normal inverse subsemigroup, whatever that should mean, and you can actually form a quotient. This is the one place where actually knowing inverse semigroup theory was useful to me, because I did come from inverse semigroup theory, I guess. And what turns out is that there's sort of a functorial equivalence between these kinds of exact sequences and twists of ample groupoids. So if you take groupoids of germs or groupoids of ultrafilters or whatever, then this thing will turn into a twist. And conversely, the twist will turn into one of these things. Of course, not every exact sequence of Boolean inverse semigroups come this way. This guy has to be the right Boolean inverse semigroup. And there's an inverse semigroup cohomology theory introduced by Lausch in the 70s, and these actually classify twists. Nobody knew what they were good for until actually Pitts and Danzig used inverse semigroup Lausch cohomology in the case of Cartan pairs of von Neumann algebras, and now we're using it again. And if A and B was a groupoid pair and satisfying the local bisection hypothesis, and then you take this exact sequence of inverse semigroups, and then you take the groupoids, you get back to where you twist that you started with. And it's the fact that you can recover this exact sequence is almost the same proof I gave for group algebras. Of course, it's harder because this is not a basis. These guys are not linearly independent, but still, it's the same idea. So the spirit's the same as the group ring case, but we no longer have that the normalizers form a basis. They just span. To go the other direction, there's a theorem of chemo, which is kind of like a Gelfand style theorem. That if you have a torsion-free commutative R algebra generated by idempotence, then it is locally constant functions with compact support on some totally disconnected space. And so you can build B, you can build up the space for B, and then you can use the conditional expectation to build the groupoid and the normalizers to build the Wahl groupoid or the ultrafilter groupoid or whatever you want to call it, and make the whole thing work. So that was kind of all I wanted to say. I probably went over by a minute or two, so sorry for that. So thanks for your attention.
Thank you very much, Ben. I wanted to ask one or two questions. So, is the groupoid? So you start with your abstractly defined Cartan pair. There is this semigroup of normalizers, and well, if you have a representation of a semigroup, and there are a couple of canonical ones, then you can form the groupoid of germs of that. And is that the way you generate the report? The groupoid?
So if you take the normalizer of the inverse of the commutative subalgebra, then that's an inverse semigroup, and you have to factor out by the inverse the normal subsemigroup of diagonal normalizers, and then its tight groupoid will be the groupoid of the twist. But then you have to recover the twist. The diagonal normalizers, its groupoid of germs is actually a trivial bundle, a trivial R cross bundle. And the normalization action of the inverse semigroup lets you kind of turn the groupoid of germs of that guy into the twist. So I had this exact sequence. So if you call the twist viewed as a central extension, sigma, then its groupoid of germs or ultrafilters is this guy. In its space. And this guy's groupoid of germs will be G. So that's what I meant by exact sequences of inverse semigroups turn into twists, provided that this guy is the inverse semigroup associated to a trivial bundle. And the local bisection hypothesis, or the quasi-Cartan hypothesis, the local bisection hypothesis is exactly what guarantees you that you don't get anything sort of bigger as far as the groupoid of germs are concerned than your original inverse semigroup, because up to kind of scalar multiplication, you basically just have bisections, or not scalar multiplication, but up to multiplication by guys in here. So that's what guarantees that you don't get too much.
And once the algebra ends up being a groupoid algebra, then, as you pointed out, it comes with a star, given by the inverse operation, right? So, and in your hypothesis, you ask that the normalizer, that is the semigroup, which is an inverse semigroup. So every element has a unique inverse. That the semigroup expands the algebra. So it's
yeah, so ex post facto,
reduced by
you're
this.
right. So if it really is a quasi-Cartan pair, so that it does come from a groupoid, then it will be a star algebra and the inverse will have to be given by the star. But that's ex post facto. We don't have to assume that to start with. That's the point. And the reason we don't want to assume that is because we want to have that if there's an isomorphism of rings, then we get everything to work out. We don't want to have to assume that we have star algebras and the isomorphisms are star isomorphisms. So if I go back to my list of original authors, Clark, Aneuf, and they had a third author with them, but it's slipping my head. They originally started with star isomorphisms of Leavitt path algebras, and they used star normalizers. And because of that, they couldn't show that a ring isomorphism was enough to recover the groupoid. So we don't want to put the star in because we get it for free. And therefore we can get a better theorem because we just require ring isomorphisms and not star algebra isomorphisms. So we definitely don't want to, and it's still unknown whether isomorphisms of integer Leavitt path algebras gives isomorphisms of path groupoids. It's known for star isomorphisms, but Carlson needs the star, and he doesn't know how to do it without the star. So it's a feature that we don't need the star, that the star you get back for free. So it's a feature, not a bug.
Are there any other questions? So I don't see any raised hands or anything in the chat. So I think we should thank Ben again.